Have you ever been listening to a loudspeaker at your local school, house of worship, or performance hall and found it hard to comprehend the sound, even though it's loud enough? Like the vocals or spoken word are all blurred together. After a while, you may feel fatigued and lose interest. Even worse, have you tried to play in a band and your floor monitor does the same thing? Isn't it frustrating? This common phenomenon can happen due to a poorly designed loudspeaker with mismatched coverage patterns across its operating frequency. One of the worst offenders are two-way loudspeakers. As seen in this typical design, the high-frequency and low-frequency drivers are radiating different coverage patterns. The high-frequency driver is placed above the low-frequency driver, and its attached waveguide is not designed to properly match the low-frequency drivers, which doesn't have a waveguide. The result is most listeners will not hear all the intended frequencies, and it will negatively impact their comprehension of the sound generated by the loudspeaker, especially with spoken words. Our brains will try to interpret the missing information and eventually become fatigued. A system operator will attempt to fix it by tuning the loudspeaker, but the inherent design flaw cannot be remedied. More modern designs incorporate a coaxial loudspeaker arrangement. This means that the high-frequency driver is located inside of or in front of the low-frequency transducer. While this design helps to reduce the size of the loudspeaker and make it easier to transport, the implementation of this design can create two problems. If the loudspeaker uses the low-frequency transducer cone itself as the high-frequency waveguide, it is not as effective or accurate as using a waveguide found in a two-way traditional design. If the loudspeaker design incorporates a physical waveguide, it can block low-frequency energy coming from the low-frequency transducer, which results in inconsistent tonal summation across the coverage area. The desire for a compact, coaxial loudspeaker design with wide bandwidth and extended pattern control has led to the creation of the Bose Beam Width Matching Waveguide, available in our new Bose AMM line of loudspeakers. Our engineers made this a top design requirement that both drivers would provide uniformity across the entire intended coverage area. So let's discuss how this was accomplished. This waveguide acts as the front baffle of the loudspeaker cabinet to maximize the acoustic volume available to the woofer, while also creating the largest possible waveguide, greatly improving pattern control. Integral to the beam width matching waveguide design are the low-frequency energy vents, specially designed to allow low-frequency energy to pass through the waveguide and align the low-frequency coverage pattern with the high-frequency coverage angles of the waveguide. This unique coaxial beam width alignment extends the coverage pattern below the crossover region, where most loudspeaker designs tend to lose directivity. The AMM Beam Width Matching Waveguide design provides a consistent horizontal and vertical coverage pattern across its intended frequency range. The result is accurate tonality and superb intelligibility with a class-leading price-to-performance ratio. To show you how impressive the AMM 112 waveguide performs, these two measurement graphs visually tell the story. The beam width chart has an x-axis that represents frequency response from 100 Hz to 20 kHz. The y-axis is coverage angle by degrees. The first chart is the AMM 112's horizontal coverage. Notice how pattern control begins at 150 Hz and stays consistent around 30 degrees off-axis for a total of 60 degrees, even through the crossover point to 20 kHz. Plus, you can visually see the entire frequency range and what the AMM 112 is capable of. This proves just how well the AMM line is designed for multi-purpose use cases. It truly maintains excellent pattern control horizontally and vertically, either on its side or not. You can confidently use it as a front-of-house, monitor, or fill solution. That's it for this tutorial. Let's focus on what you just learned. Traditional two-way loudspeaker designs are negatively impacted due to mismatched coverage patterns attempting to use the low-frequency cone itself as the high-frequency waveguide, or inconsistent tonal summation across the coverage area caused by a physical waveguide blocking low-frequency energy from the LF transducer. The beam width matching waveguide alleviates these issues by acting as the front baffle of the loudspeaker to maximize the acoustic volume of the woofer while greatly improving pattern control. Low-frequency energy vents found in the beam width matching waveguide allow low-frequency energy to pass through the waveguide and align the low-frequency coverage pattern and high-frequency coverage angles of the waveguide. Whether you are using the AMM 108 or AMM 112 as a monitor, fill, or main, you can be assured you'll have an incredibly straightforward user experience due to the benefits of the beam width matching waveguide. Thanks for taking the time to learn about the Bose innovations, and be sure to check out the rest of our AMM tutorials in the Learning Center.